Hey everybody, welcome back to another round of physics, and yeah, let's get going. This will be the last video that kind of deals with these integrals of surfaces, but part of the reason why I keep doing these, or I keep adding more and more of these, is that it's really important for you to see the different coordinate systems. It's really important for you to get exposure to all those different types of possibilities because they'll keep coming up as your career progresses. So introducing them now, start getting familiar with them, but then as you see them more and more frequently, you'll get more and more comfortable with them. So yeah, I didn't want to leave any stone unturned. So last time we were dealing with some two-dimensional surfaces, and I'll say in particular we were talking about 2D and polar. And what makes that particularly easy is that the circle that we're dealing with, that circle is still flat, if you will. It's a piece of paper. And then we talked about centering our coordinate system, say an x component, or the x direction, the y direction. Of course, the z direction will be out of the board for right-handed purposes. And we talked about finding a little area element in that coordinate system. And we know that area should be something like a length times a width. And so in Cartesian coordinates, we'd probably end up doing something like a dx dy. But that's ill-suited for these curved surfaces that we're dealing with in the example problem. Now, it can be done in dx dy, but as I hinted at in the last video, what will end up happening is if you do this dx dy, those two variables are no longer independent of one another. In other words, there is a connection between the x components and the y components, and you already know that connection. It is the radius of the circle. And so the problem, what will end up happening, is that rather than the limits of integration being set values, constants, the limit of integration will end up becoming a function of the other variable. So as I have it written here, x would be integrated first, y would be integrated second. And so x would end up getting integrated from 0 to the function r squared minus y squared square rooted. So you would have to perform the x integration, and then you could integrate y from, say, something like 0 to r. But in polar coordinates, this process is rather straightforward. We argued that the area is a length times a width. Well, the width here is a small step directly away from the origin, which we refer to as dr. And then the length was the arc length of that small section associated with a very small change in angle d theta. And so at the end of the day, we had something like r dr d theta. And because of this setup, r and d theta are independent variables. And so one, we could run from 0 to r. The other one, we go from 0 to 2 pi. And then the integrations become, for lack of a better term, less involved. We'll put it that way. Good. Well, I thought that we should probably deal with a couple more 2D surfaces. So again, we're going to work on 2D surfaces. But unlike the previous time, where that 2D surface was on a flat piece of paper, here we are going to work on a 2D surface that in itself is curved. Now, what do I mean by that? For example, here I have a piece of paper that I put into a tube. I rolled it into a cylinder. And I think we would all agree that if we take a cross section of that cylinder, we'll end up with a flat surface, namely a circle. But what happens if I'm interested, rather than the cross section, what do I do when I'm interested in finding a patch of area on the surface of the cylinder? In other words, let me go ahead and draw that in. But I'm interested in finding a patch of area on this curved surface. And you might already have some idea about how to do that. I will use this to introduce a couple of new three-dimensional coordinate systems. So the first one, and you can imagine, the first coordinate system is called cylindrical, which is namely involved with cylinders. And in the grand scheme of things, it's not too much different than that two-dimensional polar. In fact, two of the three coordinates used in the cylindrical coordinate system directly correspond to the polar coordinate system. So cylindrical, now I will draw it in, I'll try to give us a nice three-dimensional drawing here. Or I'll call this X, I'll call that Y, and I'll call this Z. The only reason for that is that we usually think of polar as being in the XY plane, and I wanted to be easier to draw. So polar, as I've said already, we are used to thinking about polar as being some circular object in the XY plane. So I'll go ahead and draw that in as a giant circle. And we know that any location on that circle can be given by an R coordinate and a theta coordinate. The cylindrical coordinate system, which is three-dimensional, adds a third variable to that, namely the distance above the XY plane, which we already have a coordinate for. That's called the Z coordinate. And in fact, this Z coordinate in cylindrical is exactly the same coordinate that we would use in Cartesian. And that should make some sense. If I get an R distance, how far away from the origin, I'm told how far around the circle, then I just know how far up in space. There's my Z coordinate. And so you can see why this might be helpful if I actually have a full cylinder, how that might be helpful in determining locations in space. I want the surface of the cylinder. And you already know the answer, right? Because you could imagine this is a piece of paper, a flat piece of paper that I've rolled into a circle. And so you could think of, you could think of the length of the piece of paper as being the circumference. And if I take that circumference and multiply by the height of my cylinder, then you have something like a quote-unquote length times a width, and that will give you the area. So right away, we know the surface area of the body of a cylinder. There you are. We know that the surface area, I'll call it A surf, is equal to 2 pi r, where r is the radius of my cylinder. There we go. Times some height, h. Well, let's go ahead and practice how could we get that using calculus and double integrals. And the whole thing boils down to, again, as we've discussed, we need to come up with some expression for the small area, infinitesimal area drawn on the surface of my cylinder. Now, if we're thinking about our cylindrical coordinate system, we know that, okay, we have the XY plane, that's the base of the cylinder, my hand. Okay. And so a tiny step in this direction is simply dz. The problem I have, so we know that we have one of these. The problem I have is unlike what you see here in the picture, or maybe I need to emphasize it a little more, that piece at the top, this piece at the bottom, they are not straight lines. They are, as you can see from a top view, that piece would be actually undergo a curve. And so I need, again, to come up with some expression giving me the infinitesimal arc length on the body of that cylinder. And that infinitesimal arc length will represent the width of my little square. Well, you said, oh, wait a minute, Greg, I've already used that. I know that an infinitesimal arc length associated with a small angle is r d theta. And in fact, you can see it in the xy plane. I need some infinitesimal arc length here. And so that's d theta. And so at the end of the day, we get that our small differential area on the body of the cylinder is, I'll capitalize this since we're set at a known distance away from the origin. So I was thinking up here very generic. Now I'm thinking very specific for this example. We have something that says r d theta dz. Well, let's go ahead. Let's go ahead and set up the limits of integration so that we can get the surface area of our entire cylinder. So go ahead, take a minute. First of all, you notice that we have two differentials, and so we are going to need two separate integrals. And for sake of consistency, I'll leave it as d theta dz. Okay. Go ahead. What are the limits of integration for theta? What are the limits of integration for z? Okay, good. Well, presuming that we're doing the entire surface area, the theta integration should go from 0 to 2 pi. And again, I'll re-emphasize the reason that we have to use it in radians is because radians are the appropriate unit so that when we take an angle times the radius, we get a distance, a displacement, an arc length. I know you didn't forget that, but I was just checking. Z? Yeah, we said, hey, the body of the cylinder will say that it's a total of height h. And so the z integral should go from 0 to h to encompass the entire cylinder. Well, now we're off and running like a bale of turtles. We recognize that r is a constant, and as a constant, we can pull it outside the integral. And just for consistency, even though we could perform either of these integrations first, since they are independent of one another, we can swap the order of integration and it doesn't change the answer. But for consistency, we'll go ahead and integrate the theta one first. So we get theta from 0 to 2 pi. And then we have dz. We do upper limit minus lower limit, and we notice that we get a 2 pi. So we have 2 pi r integral from 0 to h of dz. Of course, the integration of dz is just z. And so at the end of the day, we get that the area is 2 pi r z evaluated from 0 to h. Yeah. And we obtain the answer that we already expected, that the area of the body of the cylinder is simply 2 pi r, circumference of the cross-sectional area, right? Take that, slice it, you get a circle, 2 pi r times the height of the cylinder. All right, good. Excuse me. Well, I guess we better go the other way, right? So there's one other two-dimensional surface that I want you to be thinking about, and this one we will use several times when we get into Gauss's law. Okay? And that idea is the surface of a sphere. And the issue is, again, we would like to find the, will this draw? This might not draw very nicely. But again, we need to find the expression for an infinitesimal patch of area on the surface of that sphere. But here we have to recognize that none of the edges are straight lines, right? So what's going on here? Well, you can imagine that some distance from the origin, and I take a small angle going downwards. So this red line is some constant value r, and so I sweep a circle going downwards, say in the zy plane. But in addition to that, you could imagine that that r also sweeps back and forth. So imagine I take this r and I project it down into the xy plane. And that r also sweeps back and forth in the xy plane at some angle. Here we go. Right, some angle here as well. And so the combination of sweeping down in the YZ plane and sweeping back and forth in the XY plane, you get this kind of curved surface. That one doesn't look too curved. Let's curve it. There we go. You get some sort of curved surface. And we want to figure out what's the expression for the small area element that's represented there. We've already called this angle in the XY plane. That's what we were referring to as theta. Good? And of course, r, you could think of r as being the distance from the origin to the location in space. And so this coordinate system, spherical, is very much related to the polar coordinate system as well. You can think of, if you did spherical in 2 dimensions, you would end up with this polar coordinate system. So cylindrical and spherical, in 2 dimensions, they look the same. In 3 dimensions, they look different. And the spherical coordinate system, indeed, we deal with 3 things. We deal with r, how far you are from the origin. We deal with an angle in the xy plane. And then the third angle is something called the azimuthal angle, or sometimes the polar angle. In this picture, the polar angle is the angle between the z direction and the location that you're looking at. So that's what I've called phi here. Of course, this angle in the xy plane is theta. And as I've already mentioned, a small change in the xy plane will be referred to as d theta. A small change in the polar angle will be written as d phi. And so you can imagine that our area element will be some combination of a small change in the angle in the xy plane and a small change of the angle in the zy plane, for example, the polar angle. How we're going to represent this. Now, the first one, this small change in phi, you notice as I have drawn here, the little arc length that's associated with the small change in phi should simply be the radius of my sphere times d phi. Okay, so that piece is fairly intuitive based on the drawing that I have here. Same thing right here with my little orange. Okay, I'm talking about the radius of the orange going sweeping down. The less straightforward idea is, what is the radius of the circle? So we see I need this piece now. Okay? And I notice that what that really is it's a radius, for lack of a better term, I'll put it in quotes, a radius perpendicular to the z-axis that's sweeping back and forth. Or maybe I should say it's the component of the radius perpendicular to the z-axis. Again, in my little example here, if I take my little orange, okay, the issue is that I need the radius of that circle. You notice that I took this and I cut it right along there, and the arc length is the radius of whatever this circle is, okay, times that small angle. To get that, again, we notice that we need to take the length of r and multiply by the sine of phi to get the component of r perpendicular to my z-axis. Okay. So this piece would be r sine phi. Okay. And then, don't forget, we still need to multiply by that small angle d theta. So for that up-down one, we had r d phi. For the back into the page rotation, we have something that says r sine of phi to make sure that we have the right radius for our circle. And then we multiply by our small angle d theta. Boom, we're done. We have the expression for our infinitesimal patch of area on the surface of our sphere. And so now we're off and running like a bale of turtles. Let's go ahead. Let's go ahead and integrate that expression to find the total area. We'll say the total surface area of a sphere. Now again, we have two differentials, so we have a double integral. R is a constant, so we can pull that out front. So we end up with an r squared. Now notice sine of phi isn't a constant. Of course, you knew that. We have to leave that inside the integration or the integrand. And we'll go d phi d theta. Go ahead, write down the limits of integration for me. Good. So d phi, that is our polar angle. And we notice that the polar angle is 0 when it corresponds to the z-axis. And it can sweep all the way around until it hits negative z. And so we say that that polar angle can go from 0 to pi. So imagine taking that radius, say the length of my pen, okay, and that polar angle can go from here and it sweeps all the way down to there. Now you can imagine taking that semicircle, and the next thing we're going to do is rotate it 360 degrees, 2 pi radians around the z-axis. And you can see that that will form the entire surface of the sphere. And so that that theta measurement goes from 0 to 2 pi. All right. Well, now all that's left to do is for us to integrate. Of course, we know that the integral of sine has negative cosine of phi. Good. And let's go ahead and evaluate at the upper and lower limits. We get r squared, the integral of 0 to 2 pi of negative cosine of pi. And we should be very careful here. The temptation is always, 0, it means it's 0. So we should stop. Okay. Cosine of pi is negative 1. Good. Cosine of pi is negative 1. So this is negative 1. And notice we have a negative, which means it's positive. Cosine of 0 is 1. And so we end up with something that says 2 times r squared, the integral from 0 to 2 pi of d theta. So I know what the integration of theta is. That's just theta from 0 to 2 pi. And evaluating that out, we see at the end of the day that the area of the surface of a sphere is 4 pi r squared. Pretty cool, huh? Of course, I suspect that many of you already knew that from, say, a geometry class. Okay. This is just a way to do it, again, thinking about integrations. And as I said at the beginning of the video, the purpose was not necessarily to get those final results. The purpose was to introduce that idea about how to get those small differential surface elements. So go back, make sure that that kind of makes sense about why we have to do that. It's the idea that we're dealing with curved surfaces now, so we have to be careful about how we express the arc length elements when we're dealing with these kind of different surfaces than straight boxy. I think that's it for everything. We won't go into volume measurements. We won't go into the rest of the stuff. We got to save something for, Phys 332, some upper level physics class that deals with electricity and magnetism. So, but that will be enough by far to succeed both in this course, probably to succeed in several courses after this. So anyway, I will leave it at that. I thank you for your attention. Keep up the good work. I'll see you next time.